21 grams, this is supposedly the weight of the soul, which was measured in 1907 by the American scientist Duncan MacDougall. His experiment consisted of measuring the weight of dying patients before and after their death to see if there was any change in the weight that could be attributed to the soul leaving the body. On specially modified scales where the patients lay, a weight loss of 21 grams was recorded in one patient at the moment of death. In the lay public, this experiment is often regarded as the irrefutable scientific proof of the existence of the soul. But in fact, it does not prove much. The weight loss was not consistent, sometimes there was no loss at all, and more realistic explanation is perhaps the loss was due to the release of gases or something else. This experiment though illustrates that the question of quantifying the soul or somehow bringing the soul into our physical world has interested us for ages. And so I thought I would attempt a similar quantification with the help of modern science and graphic visualization. What am I really going to quantify if I want to quantify the soul? Well, in my worldview, it is the brain and its workings. If you get a disease destroying your brain, you gradually lose not only your memory, but also your ability to think and ultimately the basic essence of who you are. So what is the brain? The brain is a mass that weighs approximately 1.5 kilograms. When you think about it, that 1.5 kilograms is made up of cells, and that's a lot of cells. There are a whopping 86 billion neurons, but that's just neuronal cells. We have another 85 billion non-neuronal cells in the brain that take care of immunity, neurons' health, and much more. If every single cell in the brain were a star, we get approximately the number of stars in our galaxy. Speaking of neuron cells, we have all probably seen some picture of a neuron. The body, the long projection called the axon, and the short projections called the dendrites. However, the length of neurons varies considerably. In some areas, neurons are about 1.5 centimeters long. In other areas, it can be as long as 10 centimeters. We can get a better sense of the length of the cells if we try to visualize a situation where all neurons are lined up next to each other, forming a string. Try to guess how long the string would be. Would we reach from Germany to France? Maybe from Germany to the US? In fact, we would reach the moon. And back. We'd get a string about 800,000 kilometers long. And that's really a lot, all packed neatly here in these 1.5 kilos of mass. Now, you've probably heard of synapses, places where two brain cells communicate with each other. Most often, one cell releases various chemicals and the other can register them with its receptors. Everything you do, everything you feel, everything you think about, your whole reality, your soul if you want, is the result of the intricate communication of these connections. If your mind didn't get blown away by the length of your neurons, it probably will by the number of synapses in your brain. An incredible number of 100 trillion synapses. That's 100 followed by 12 zeros. Let's say each synapse were represented by a simple LED light bulb. Suppose that light bulb would occupy 25 square centimeters. All the synapses would then occupy a whopping 250,000 square kilometers. That's roughly the size of the entire United Kingdom. How much energy would these light bulb synapses consume? A single light bulb, which I would normally buy online, needs about 60 watts per hour. If we left them on for 1 hour, they would consume 6 terawatt hours. If we convert that to the units used in the release of energy in explosions, we get about 5 megatons of TNT, which is roughly 300 times more energy than was released in the Little Boy or Fat Man nuclear bomb explosions in Hiroshima and Nagasaki. At the same time, it's roughly 1/3 of the Castle Bravo, the largest US nuclear bomb ever tested, and roughly 1/10 of the Tsar bomb, Russia's largest nuclear bomb ever tested. However, these energies are completely fabricated. Hi, if you like the content that you're just watching, don't forget to subscribe, comment, like, and all this kind of stuff that helps the YouTube algorithm. It's a new YouTube channel, so it would really help me. Thank you very much, and let's go back into it. Our brain doesn't need that much energy in any case. So how much does it need? Despite being about 2% of the total body weight, the brain eats up to 20% of all energy.
In one day, we consume approximately 2,000 kilocalories. That means that the brain takes roughly 400 kilocalories. In 1 hour, that's about 16.6 kilocalories, which is roughly 70 kilojoules, and that's approximately 19 watts.
In other words, for 1 hour of brain power, I could light a 60 watts light bulb for about 20 minutes. The brain is extremely efficient when it comes to energy consumption. Just think about it. Every second your brain is generating a beautiful high-resolution image. Close your eyes and imagine a jumping German Shepherd. Can you see it? It works immediately. Yet, generative artificial intelligence needs ideally large server rooms with GPUs to generate video from text, and even then, we can't do it in real time, just like our brains can. Let's talk more about communication in the brain. The most common communication is through chemical compounds, neurotransmitters. Let's suppose we could throw the whole brain into a blender and isolate the various components of brain communication. If we took all the neurotransmitters, and there is more than 100 of them, we would get about the volume of a teaspoon. That's it. All communication is the volume of a teaspoon. Dopamine, for example, would have the volume of roughly a small drop. Isn't it interesting that this is your motivation, your enthusiasm for food or sex? Calm mood, stress response, neuroplasticity, that lies in a drop of serotonin, roughly half the size of dopamine. The body's arousal, that's a drop of norepinephrine. By far the largest drop is the drop of glutamate. Not so well known, but it is the most common neurotransmitter that triggers a nerve impulse. On the other hand, GABA is responsible for inhibiting the signaling. The rest are other chemicals such as acetylcholine, histamine, and peptides that by their subtle actions ensure that your body runs properly. I just managed to shove our entire soul into matter. Lots of neurons, lots of signaling, some chemicals, and the result is the human soul, or more scientifically, consciousness and ego. But we can probably agree that this lacks the proper sense of satisfaction. I don't feel that I have really understood the human soul by this dismantling action. It's a bit like trying to understand the beauty of the tide, the noise on the beach through the dismantling of water into HO2 molecules. If I do that, I'm not even one step closer to understanding the beauty that arises at a higher level when all molecules interact with each other according to the rules of nature. So, for example, I could describe love as a drop of oxytocin and a few activated regions in the brain. But I would be no closer to understanding the millions of books that have been written about it, the hundreds of battles and wars that have been fought because of it, the music that has been composed because of it, or the suffering that it causes. I'm touching here perhaps the most difficult problem in philosophy, the problem of emergence, or how simple systems give rise to complex ones, including human consciousness and character. So how much does the human soul weigh, whatever we mean by that? I think this question is meaningless. How much does a beautiful symphony weigh? Close your eyes and listen. How much does it weigh? I have a bold thought. Maybe, just maybe, these phenomena, like the human soul or consciousness, love, images, emotions, don't really occur in our material reality where we can weigh things. Where do they live then? This is the question I explored back in my early days of my psychonautic past. Where are we? If you were to open my skull, you would find a bunch of neurons, a bunch of matter, but you wouldn't find me. You wouldn't find the sound of the symphony that can be heard. You will find neurons and their activity. But where is the sound? Where are the colors that you can see? On one hand, we admit that the soul or consciousness is tied to our brain. On the other hand, no matter how much we chop it up, shred it to pieces, juice it, we won't find what we are looking for. As you lie in the bed tonight and various images flash through your mind, try to think for a moment, where are they actually? I'm Peter, and this is BeWise.